So this lesson is on Arrhenius equation. This is basically the mathematical concept or the quantitative analysis of how changes in temperature, adding a catalyst affects the rate. So we're dealing with numbers here. The main learning objectives here are performing calculations using the Arrhenius equation. We will explain what this is, and then understanding that the equation can be rearranged into this form. I'll go over all of this next in this short presentation. Okay, let's start with this. Now you need to refer back to your year 12 notes on the effect of temperature on rate. So we've done Maxwell-Boltzmann distribution. We know when temperature increases, particles gain kinetic energy, they move faster, they collide more often, there are more successful collisions per unit time, per second, per minute. Therefore, more particles will collide with energy greater than activation energy. Now, what's the relationship then between temperature and rate constant? You don't need to know these figures, but you need to know this graph. So you can see from this graph here that temperature and rate constant are not directly proportional. If anything, when temperature increases, rate increases by much more than that. And rate constant is dependent on temperature. So rate constant will increase with temperature. That's the key thing. The higher the temperature, the larger the value of rate constant. Okay. We have already covered Boltzmann distribution curve. Just to reiterate on that point I've already highlighted. Look at the Boltzmann distribution curve. These should never touch the x-axis. They actually don't. It's not very clear here. But you can see at 300 K, you've got much more particles that have energy above activation energy. This is the additional particles at 300 K. At 100 K, you've only got this much particles above activation energy. Now let's move on to Arrhenius equation, because that's what we really want to look at. Therefore, you will be given this equation. K equals A times E to the minus EA over capital R, capital T. Now let's first of all describe or define what each of these letters means. K is the rate constant. A is known as Arrhenius constant. It has same units as K. In most cases, the units will be per second. It is also known as a pre-exponential factor. EA is activation energy, and please note the units, joules per K per mole. R is the gas constant, which you already know, 8.31, that value will be given. T is temperature in Kelvin. So what's this E? On your calculator, so I normally use the Casio calculator. I have my on button, and then below the on button I have a button called const, and then below that I have a button which looks like IN, but it's actually LN. On top of that, in orange, you will see e to the power of x. So if I press the shift button on my calculator and press EX, so if I do shift LN, I will see the letter E appearing. So that's how we use this on the calculator. Right. So how do we rearrange, first of all, for EA, for A, for T? My advice is pause the video now, rearrange this yourselves, and then see the answers at the moment afterwards. So now I'm going to go through this in terms of rearranging. So just to reiterate, pause the video, rearrange, and then I'm going to go through the solutions. So in order to rearrange for EA, use the following equation. You have to rearrange this equation into this format. Natural log of k, natural log of a minus EA over RT. I tend to move the negative to the opposite side, so it becomes EA over RT equals natural log of A, move natural log of k to this side, it becomes natural log of k. Now it's entirely up to you how you do rearranging of equations. Whatever you've been taught at GCSE, just use that. So EA becomes natural log of A minus natural log of k times R times T. That's how I would rearrange for EA. To rearrange for A, okay, so for A, I would use the first equation. And A becomes K divided by E minus EA over RT. That's how I would rearrange for this. Now remember, you have your own methods of how to rearrange, and you can just rearrange how you feel comfortable. Okay, just gonna rub off few things and then do a rearrangement of T. So how do we rearrange for T? Well, we've already done this. We've already said EA equals natural log of A minus natural log of K times RT. So if you've got that format, then T simply becomes EA divided by natural log of A minus natural log of K times T. So that's how you would rearrange these equations. Again, please practice this because you do need to practice how to rearrange for the equations. I'm just going to rub everything off, okay, and then move on and show you what's going to happen next. Okay, right, now let's explain what do we mean by let's go into the Arrhenius equation in a bit more depth now. So the Arrhenius equation is K equals A E to minus EA over RT. Okay, it's not letting me type in EA for some reason. Okay, it's K equals A. Okay, right, this term, this E to the minus EA over RT, the fraction of molecules with energy greater than activation is given by that term. Okay, now note, rate constant is mathematically linked to temperature. Now the equation, as I'm reiterating, is given. Please also remember this equation. This equation is a rearranged version of the Arrhenius equation that's given. This equation is like a linear format, and we will go into this in a bit. Okay, so what we want to do is, let's do a calculation. The effect of change of temperature, let's prove that rate changes with temperature. What happens if you increase the temperature by 10 degrees from 20 to 30? Okay, now because all we're doing is temperature is changing, we will assume that A is 1 because the exponential factor is not changing. The A Arrhenius constant is not going to change. So what we want to work out is we're going to do K equals 1 times E minus EA over RT. 10 degrees is 293. So I want to do the calculation with the 293. My advice on how to do the calculation. So what we will do first is let's work out EA over RT. And to do this, now activation energy is given as 50 kilojoules. So that becomes 50,000. Divide that by 8.31 times 293. That equals, so just note the way I'm doing this calculation. 8.31 times 293, and that comes to 20.535. At this stage, minimum of 3 significant figures. My advice is 4 or 5 significant figures at this stage. If you round off your answer in the calculator, make sure you round off clearly. Now I'm going to do this. Next, work out E to the power of minus 20.535. So I'm going to press the shift button on my calculator. So I'm pressing shift, I'm pressing natural log, and then I'm just going to type in minus 20.535. So minus 20.535, and I get an answer of 1.21 times 10 to the minus 9. Okay, that's K per second. That's the simple calculation. Okay. Now let's do the same thing at 303. So just to show you what I've done, I worked out that first, then I did the next bit. I'm going to do the same thing again. I'm going to work out, do not put things into a calculator straight away. Work out 50,000 divided by 8.31 times 303. Work that out first. So 50,000 divided by open brackets 8.31 times 303, and that now comes to 19.8578. Okay, so now E minus 19.858, same concept, shift natural log minus, and then 19.858, get an answer of 2.38 times 10 to the minus 9. Now let's compare. You got 1.21 times 10 to the minus 9 at 20 degrees Celsius, which is 293 Kelvin. You got 2.38 times 10 to the minus 9 at 10 degrees increase. Roughly, that's twice as much increase. That means a 10 degrees increase has doubled rate. That is your quantitative analysis, and that is the calculation you will need to do. Okay? So, what about doing the same calculation with the catalyst? So what we're going to do now is at 293 Kelvin, we add a catalyst. This reduces the activation energy to 25 kilojoules per mole, which is 25,000 joules per mole. So let's do the calculation. Okay. Again, please note my advice is work out e to the minus, work out 25,000 over 8.31 times 293 first. Just reiterating, because this is going to help you to keep it simple and not to make any mistakes in calculations. Excuse me. 10.268, then E minus 10.268 comes to 3.47 times 10 to the minus 5. Clearly you can see the rate has increased by much more. So the rate initially was let's see. So you will see that the rate's gone up by almost 30,000 times. I'm just going to go back just to yes. So the rate at when activation energy was 50,000, the rate was 121 times 10 to the minus 9, or the rate constant. That's with activation energy at 50,000 joules. At 25,000 joules of activation energy, the rate has gone down to has increased 3.47 times 10 to the minus 5. That's almost 30,000 times increase in rate. And so let me rub this off. Sorry. So you can see here that the rate has gone up by 30,000 times. Just a factor change. All you need to do is to work out the factor change. 3.47 times 10 to the minus 5 divided by to the minus 5 divided by 1.21 to minus 9, and you get a change of almost 30,000. Okay, divide by 121 times 10 to the minus 9, that's almost 30,000 times change. Okay, finding the activation energy for reaction, again using the formula method. So another example for you. Calculate the activation energy for the reaction. This time they've given you the Arrhenius constant. You know the rate constant. You know temperature is given, R is given. So identify what you know. Write the equation. So K equals A E A over RT. Remember to work out EA, rearrange like this. Rearrange for EA. EA equals natural log of A minus natural log of K times RT. Again, my advice now, work out this separately. So what I'm going to do first is I'm going to work out natural log of A. So I'm going to press the natural log button on my calculator and then type in 5.25 to 5. Then I'm going to do minus, open brackets, type in natural log, and now natural log of K is 3.36 to minus 4. That value comes to 21.17. Going to multiply by 8.31 and 298. So times by 8.31 times by 298, and I get an answer of 52,424 joules. Going to leave the answer in kilojoules. So 52.4 kilojoules to 3 significant figures. Please note, I worked out natural log of A by doing natural log times natural log and then 5.25 times 10 to the 5. Then I did minus. Then I opened my brackets and did natural log 3.36 times 10 to the minus 4. Close my brackets, did equals, and I got an answer of 21.17. If you do the calculation in this way, you keep it nice and simple, you don't make mistakes. Okay? And here's the working out for you. Okay? Again, there's another worked example. My advice is pause the video here, do the example, and then see the working out. So I'm going to pause for 10 seconds. You must pause the video here. Okay, so rearrange and work out activation energy. Again in a similar way. Okay, so there's another worked example. Question 3, again pause and work through the example. Please pause the video here. Do the example and then move the video forward so you can see the examples. I've already done these examples with you, just different numbers. Okay, so again you will see the answers. Same here, question 4, pause the video, do the question yourself, and then compare with the answers. So that's basically how to do Arrhenius equation, how to do the calculation. Now about the graph. Now this format, natural log, is in the format of y equals mx plus c. There's an expectation that you would plot a graph. Natural log of k is on the y-axis, that's y. X-axis is 1 over t, and then gradient of the line, so your gradient of the line is going to be EA over R. So to work out activation energy from the graph, you have to multiply gradient by R. Okay, let's show you an example. So this means the activation energy and Arrhenius constant can be found from plotting the graph. Okay, you can work out natural log of A from there. You can work out activation energy from the gradient of the graph. Here's an example. We're given temperature, we're doing K. So what we have to do here is we have to have another two rows, or call 2 rows of table in which we work out natural log of K, and we work out natural log of and we work out 1 over t. So can you see? So I'm going to work out natural log of k. So basically natural log 4.41. You can pause the video and do this yourself. Work out 1 over t and see if your answers match mine, like that. Now we're going to plot a graph, and the graph is going to look something like this. And I will do the gradient of the line, and the best way to do the gradient of the line is use the biggest area possible to do the gradient of the line. So change in y is that height there, so I'll call this dy, that's dx, that's the gradient. To work out EA, you're going to do gradient times 8.31. Okay, there's another example. Take some graph paper, work this out yourselves, okay, and see what answers you get. Okay, and then just show me in class. And there's an example. Now exam question 9.1, you will need graph paper. Please work this out, plot this on the graph, and see what answers you get. The working outs are all there. Pause the graph, pause the video, and work through the graph. And there are numerous examples which you can work out. Some of these are genuinely exam questions. So hopefully you found this video useful.